So I'm going to introduce our speaker today, Peiyu Cao. Peiyu Cao is a postdoctor at Cornell, focusing on the livestock sustainability and climate change. And so I'm really looking forward to hearing about his research. And Peiyu Cao, the topic, the title of the topic of Peiyu today is uh, green, cropland greenhouse gas emissions. Uh, uh, Around the 2020s. So it's a new published research on nature climate change. I think it's 3 weeks before. So it's still hot print. So I will pass the mic to Peiyu and to introduce his uh, research.
Thank you, Yu. Thank you for the introduction. Hello, everyone. My name is Peiyu Cao.
Excuse me, Peiyu, would you mind to share your screen?
Oh, yeah. Can you see my slides?
Yeah, it's perfect.
Okay, great. All right. Yeah, thank you for the opportunity to invite me to give this talk. I'm very glad to be here seeing you all to introduce our work on the global carbon emissions circa 2020. So first, I want to give you a big picture about our work. We estimate the greenhouse gas emissions from the cropland of the six sources circa 2020 at a global scale and a 5 arc-minute resolution, which is around 10 kilometer, covering almost all temporary and permanent crops. And we group them into 46 classes based on the MAP-SPAN crop definition. And these six sources includes the N2O emission from those three nitrogen inputs, synthetic fertilizer, manure, and the residue, and methane emission from rice, flooded rice, and then emissions from the dried peatland for crop, as well as the crop residue burning on the field. As you can see, we follow the latest or the most refined approach by IPCC. This is the workflow that we use to develop our activity data to apply to this IPCC approach. You can see mostly we compile multiple data sources from including those remote sensing, national inventory, and some modeling data. We use the MapSpan 2020 as our base map for crop distribution. And then based on that, we've built up pieces by pieces. We merge them together to get this harmonized input data sets. So we start from those national or either national level data or spatial explicit data, and we gradually harmonize them, compile them, do the quality control down to the same resolution at 5 arc-minute. And you can see they have some interactions or interlinks. For example, the rice, to estimate the rice methane emission, we need the organic amendment. So we combine that manure application with the crop residue application as the organic amendment. So you can see they have some um, links. So let's first dive into the N2O emission from those three inputs, three nitrogen inputs. So as you can see, this figure shows different pathways of N2O emission. So first, let's look at the central part. So first, there are three major nitrogen inputs: synthetic fertilizer, manure, and crop residue that being left on the ground. So when those nitrogen inputs be applied to the cropland soil, through the nitrification and denitrification, the soil can direct emit the N2O back to the atmosphere. There are other, there are two different indirect emission pathways. On the left is the nitrogen can be volatilized to the atmosphere as ammonia or NOx, and then those nitrogen gases be deposited back to the soil and then re-emitted as N2O. That's one pathway of indirect emission. And another one is on the right. The nitrogen in the soil can be flushed out or leached out from the soil to the water bodies, and there they can be re-emitted as the N2O. So that's the other indirect N2O emission pathways. We account for all those pathways following the IPCC approach, indicated in those red boxes. So IPCC used the metadata analysis plus the linear mix model to quantify the emission factors within different regions. So say by climate zone, by different crop types, by different water management. So based on that approach, we develop the key inputs showing in the blue box. Those are the major activity data we developed to estimate the greenhouse gas emissions, including the climate zone, the rice water regime management, irrigation management, runoff leaching, and those spatial nitrogen inputs. So first, let's look at how we develop our fertilizer maps. We develop fertilizer application rate data by crop and by type. So first, we use the IFAS data, which is National Crop Specific Fertilizer Application Rate, as well as the consumption. And we clean up all the data and group them into 46 crops. And then we use the national total fertilizer use by Fallstat to do the national control. And then we did a further control at subnational level. We collect those subnational data from 14 nations to downscale the national crop specific to subnational crop specific fertilizer use. And the final step is we develop the fertilizer type information for each country from IFA and Fallstat. Then we use that information to split the annual fertilizer into different fertilizer types. As you can see, those colored administrative units are those subnational data we collected from different resources. It covers 14 nations, accounting for over 80% of global total fertilizer use. This is an example of our final fertilizer data map. So, for example, for the figure A on the top left, it shows the urea application rate for maize. Then we develop our manure nitrogen input data. So first, we estimate how much manure production from the different animal species around the globe. So we based on those animal distribution, production systems, herd dynamics, which is more like age groups, with the specific nitrogen excretion rate. We estimate the manure production, and then we consider different loss ways or uses of the manure to disaggregate the total production to different usage. Then we get how much manure has been applied to the cropland. Due to the lack of the crop-specific information, we assume all the crop within that same pixel receive the same manure application rate. And then we also reconstruct the crop residue for crop. So well, first we start from the map span. It's a 5 arcmin spatial map. It it has the crop specific yield data. Then we start from that yield data to um, develop the crop biomass, and then we piece by piece to disaggregate the usage for feeding, for fuel, for biogas, for bedding. We also consider the trading of residue across pixels to fill up those deficit. Um, so then last step we get how much crop residue left on the ground, and then we use that crop specific nitrogen content of residue to get how much nitrogen has been incorporated into the field. This is the illustration of our three nitrogen inputs. You can see the distribution varies among those three inputs. So after we develop uh, the data for those three nitrogen inputs, we apply the IPCC approach accordingly to get this emission by different sources, different pathways. Here I just show some stacked results. So this is the stacked N2O from all those pathways from fertilizer. You can see the hotspot of N2O emission from fertilizer concentrated in like China, India, Europe, southern Brazil, and part of the US. And it's different from the N2O from manure, where it basically follows the distribution of animal density. One note is when you look at the scale, it's different. Let me go back. So fertilizer has the largest or more intensive emissions. And the manure and the residue, they have less intensive N2O emission. So here, this is the N2O from residue. You can see it follows how different region use the crop residue or handling the crop residue. Then let's move to the rice paddy. There are many factors influencing the methane emission from flooded rice. When you look at the central part, the top figure, so the most significant factor is when the rice field is flooded, they create this anaerobic condition. Another factor, a very significant factor, is the length of this flooding period, as well as the organic amendment. So when you look at the left panel, it's matter of the water region management. So if it's continuous flooding, it creates the longest anaerobic condition that promote the methane emission. Some systems they adopt the single drainage, which they drain the rice field in the mid-season. So that kind of break this continuous flooding and break this anaerobic condition that reduce the methane emission. Some systems they adopt this multiple drainage that can significantly reduce the methane emission. And the center part, the bottom part shows if there are more organic amendment that kind of provide more source for the microbials that can also promote the methane emissions. And on the right sector is on the length of the growing season. Usually, the longer period of growing season or more growing seasons, um, the longer period of this anaerobic condition that also promote the methane emissions. So after we understand how different factors impacting this methane emission, we can follow the IPCC approach. So IPCC use metadata and also those linear mixed model to quantify the image factor under different factors, and also use the scaler to scale the image factor for different regions. So based on those information, we sum up all the necessary activity data in the blue box. So we develop this distribution of rain-fed irrigated rice, and we also develop this rice water region management and the rice calendar, and also those organic amendment. So let's dive into that. Um, the most important is the water region management, the continuous flooding or single drainage or multiple drainage or other water management that really impact this methane emission. However, when we search online, we couldn't find a very good data source. I mean, spatial information. So we went online to different national statistical agencies and FAO, United Nations reports. We scrap all those pieces of information and compile them together to collect those water management information over 80 countries for rain-fed rice system and over 30 countries for irrigated. This two maps shows where are those data available for different countries, indicated by the colored countries. This map shows the distribution of those different water management. This is for rain-fed. And then when you look at the bottom right map, that's the one management or water region, which is deep water, because it's um, frequently flooded the rice, so it has the highest emission. Um, but because it's a rain-fed, it's under natural condition, so it's changing to for those system to have a better mitigation strategies. So one suggestion could be they may shift the land use to other types to reduce the emission instead of improving any management because it's more natural conditions. And here is the um, distribution of the water management for irrigated rice. And as you can see, the figure A on the top left, which is a continuously flooding condition. So it has the highest emission potential. So those countries in like green or blue colors indicates that they adopt the highest proportion of the continuous flooding. So their mitigation strategy could be adopt like multiple drainage strategy to mitigate their emissions. So it's a more management side. And then we apply this crop calendar from these products, the rice atlas. It provides a very good graded map of number of growing season as well as the duration of each season. That's very important for us to um, estimate the emissions. With all that information, we apply this IPCC approach to get the emission from rice paddies. As you can see, the Asian countries as the hotspot of the rice methane emission, of course, because they are the major rice producers. When you look at those dark colors, that's the most intensive emissions, usually corresponding to those area adopt the triple growing seasons. So that number of growing season and the duration of growing season really matters. And then let's move to the drought period. So peatland is a type of wetland, but it has a very deep depths of organic carbon, and it's usually under the saturated or even flooded condition. To grow crop on that peatland, it has to be drained or lower the water table. However, when we drain the peatland, the soil is exposed to the oxygen that promote the emission, the decomposition of those organic matter. So that's on the left side, which is on-site emissions when we directly drain the water on site. And in parallel, when we drain the peatland, the drainage carry out those dissolved or and in dissolved organic to the ditches. So there it created like flooded condition that promote huge amount of methane emissions as well as other like CO2 or NO emissions. So that's the second component of emission, which is in-ditch emissions. So we consider all this both these two components. Or so IPCC identify those emission factors under different conditions. So, but we summarize that the most important part is to get the accurate trend peatland distribution by crop. So when we go online to search for those global peatland products, we found huge discrepancies. For example, in terms of the peatland area and the extent. For example, on the for the AFL organic soils, it has a list peatland areas on the top left. It also has a list distribution. When you look at the peat ML on the top right, it has the largest or widest distribution of peatland. So how to use this map? So which one to use? Because use any of this could create very large uncertainty. So we figure out one way to hybrid them, to combine them. So first, we use the largest distribution map from the PEAT ML, which is based on the machine learning approach. And we use that as our base or reference so that we don't miss those small pieces. Then we use the other three products as the index. We develop an agreement index using those the other three products. And we also use the UN Global Peatland Assessment, the national reports for peatland area and drain peatland area to control the total peatland area for each country. So here's how it works. So first we have that widest distribution of peatland as a reference. Then we use those three products as an index if at least two of them indicates that pixel has peatland. And meanwhile, that pixel has greater than 10% of peatland. We assume that pixel has peatland. In the opposite, we assume that pixel has no peatland. So this shows the blue and the plus red color indicates where our final peatland pixel are. And then we overlap in those the peatland extent with our cropland extent and use the UN report, national report to constrain that national area. We get this drain peatland for crop as those colored pixels. And with that, we generate this emission estimates. It follows the general distribution of the peatland, and the intensity indicates the intensity of the cropland. And lastly, we estimate the emission from crop residue burning on the field, because in the previous step, we have already um, generate the usage of crop residue for different uses. So one usage is for burning on the field. So we directly use that information to estimate the emission. So here's the spatial pattern of that emission from burning. You can see Africa has because they vary across region based on their local people's culture. You can see Africa has more. They like to burn crop residue, or that's their way to reduce the impacts of residue. So those are all those information are all spatial maps. We did some aggregation to regional and the nation global analysis. So first we did the validation. Um, we aggregate all those spatial data to national by different sources, by different gases against FAO national reports. It shows a pretty good alignment. And then we made this Sankey figure to track the emission flows from regions to crops to emission sources and to gases. When you look at the region on the left, the East Asia and the Pacific account for 50% of global total emission, followed by the South Asia and then Europe. And when you look at the crops, rice alone account for 43%. And if you add the other series, the series itself account for 65% of total emissions. And when you look at the emission sources, those three major sources from flooded rice, drained peatland, and the fertilizer, they account for over 90% of emissions. We also did some comparison between the emission intensity against the productivity of a calorie to imply some mitigation strategies. So let's first look at the left figure. The red dash line is the global mean of each index. We use this global mean to separate the whole zone into four zones. When you look at the zone one, it's the safest zone. It has a lower emission, it has a high productivities. Countries like US and Brazil, they fall into this zone. And the zone two indicates it's low emission, but it's also with low productivities. Most African countries fall into that zone. So the suggestion for them is to keep their low emissions, but improve their productivity to move their zone to the bottom. And for the zones three, it has high emission and also high productivities. So those countries in Asia and South America fall into this zone. So their suggestion is to um, keep their high productivity while lower their emission to move left. Yeah, I think that's my uh, presentation. Thank you. Um, I'd like to take any questions and also look forward to any discussions for further improvements and potential collaborations.
Okay, thank you, Dr. Cao. Yeah, it's a really insightful. So we have around 5 minutes to have a Q&A, and then we'll move into the open forum discussion sessions. So does anyone has any questions you'd like to ask? You can direct unmute yourself, or if you want to type on the chat box. Okay. So I actually have one question for Peiyu. My question is that it's pretty impressive data for the global scale greenhouse gas emission from the croplands. So I'm curious that how did you curate the data? And if we want to reuse the data, how can we access?
All the data is publicly available in the data repository, so you can direct access to any data. We have released all the data for this work.
Okay. So
But
it
if
is.
you want more
Mhm.
refinement, yeah, I can. Please contact us or reach out to us. We can do more refinement for your need.
Okay, good. So is anybody else have questions for Pei?
Yeah, maybe I have a quick question. So, hi, this is Bar. So, I go by Bar, Lindsay Barberry, and I'm at the University of Maryland currently. And yeah, first of all, thank you so much. This was just a fascinating and really exciting talk. And yeah, really looking forward to reading more of the papers, looking at the data, and maybe reaching out to you for a couple of potential collaborations. We've been working on the greenhouse gas inventory for the US. Um, Recently that I'm a part of a small team that's been working on that at the University of Maryland. And I guess my question here is like which you've covered such a breadth of greenhouse gas emission sources here globally. And I loved how when you got into the weeds a little bit with the peatland, because yeah, like looking at the different data sources that are available and just showing how there's these big discrepancies and then like your process for kind of trying to get at the best data set. I guess I'm curious, like what like when you think about across all of these different emissions pathways, like where do you see the most challenging or like the most discrepancies, in all of these sources? And yeah, what are kind of your next, like where do you think the best improvements are going to be in the next sort of iterations?
Yeah, that's a really good question. We have a lot of thinking on the refinement of the data set. As you can see, a lot of data they have, result we claim is 5 arc minute, but a lot of data they are actually their actual resolution is at subnational or even national. Like for
Yeah,
example, for the rise of water region, as national data, we just apply the national ratio to all pixels in that nation.
yeah.
So there are definitely a lot of improvement that can be done. Um, Go back to your question about pedant. Um, I think there are big description for the pedant map. Each of them, they claim they are the best. Um, but when you recently, I'm working on the uncertainty analysis for these different maps. When you really look into that global total area from different products, say FAO, it estimates there are like 32 million hectare of peatland. But when you look at the global forest watch, it estimates 76 million hectares, so it's doubled. Um, so how to map out the accurate peatland is changing because it's a matter of definition. Some organizations they assume okay if the organic matter depth is like 30 centimeter, it's peatland, but some organization they think that's too deep. We can say 15 centimeter depth is enough for a peatland. And also it's a matter of water status. So it's really changing to get the real location of that peatland. And the peatland part is the most um, critical comments we receive from the reviewer, because that reviewer is the local experts of South America. So he really doesn't agree with our map even though we hybrid all those into one, but he really criticized our distribution map. He says, "Oh, look at that pixel or that small region. There's no plant there, but your map shows." So it's really matter to collaborate with the real plant experts from different regions because they go to that place. They know if there's a plant. That's the uncertainty from plant itself. Another one is the drained plant for crop. Um, Although there could be plant, but the question is, it's been drained for this year or hundreds of years. It's drained for cropland or for forestry or grassland. How do you identify that actual location of that plant be drained for what purpose? Um, for our current work, we have to use the national number to constrain that. However, the spatial distribution within that country is unsure. So there are a lot of work to be done, maybe through the remote sensing, plus the very local experts we use, to gradually put that piece by piece together to identify those uncertainties. Yeah, I think that's hope my answer helps. I think you are mute. You're muted.
Oh, sorry. I say, is there any other questions? You can direct unmute yourself, or you can text in the chat box. So actually, I have another one for Peiyu. I noticed that for your overview map, um, the Midwest US, the cereal croplands doesn't account much comparing to the rice and pathlands. So, would you think in the aspect of the like climate mitigations, does these regions have a high potential? Because these regions has already been invested for the conservation practice a lot and for a long time. So I just want to curious about what's your thought on it.
Do you mean the N2 emission or?
Yeah.
Okay. Yeah. Um, Actually, when you look at this map, it's weird to look at US. Um, the N2 emission intensity the hotspot should be in the Midwest. This is due to the approach by IPCC. But anyway, um, yeah, I agree with you. Like, because did my PhD in Iowa, I know many experts have already tried many different ways to mitigate emissions, apply those 4R strategies, or even use edge of field practices. I would say it's really hard to say if there's the best management practices can mitigate the mitigation there, as they have already applied good practices. Um, yeah, it's hard to answer that question. Maybe it's through the crop livestock integration and promote more recycling of manure. But that's a more systematic strategies instead of like single individual practices.
Cool. Thank you for your answers. I think that's probably the point we can like seeking for future collaborations. Yeah, Lindsay raised another question on the chat box that yeah, where was the data repositories for those data?
Yeah, I think you said that, but I missed it. Sorry.
I'll attach the link. One moment.
Okay. When Peiyu is sending the link,
So
okay, it's
here's
a link
the
for
link
paper.
to the paper, and then
Okay, thank you.
Um,
Yeah, I think the data is the point that people uh, is interesting about, and it is the data bring the people into our clusters. So I want to emphasize that we are hosting, we are running these clusters. We're seeking for like data exchange, how to like reuse the current ag and climate data is our purpose. So we will everyone to raise up any ideas or any requests that we can help each others. So I think we can end up the Q&A section here. Um, we have 10 minutes left, and I'd like to introduce guys some resources like how these clusters can provide with you. Um, First of all, in the chat box, I think Aaron has already shared the Slack channels of our clusters. I will resend again. Yeah, we have our Slack channel and email list. So we will update our latest messages there. You can share anything you want, share any ideas. Except that we have a Padlet. I will also sharing the link through the chat box. It's the Padlet. The Padlet is established for the first meeting of our cluster plan to reactive, and our class member has already write down some ideas that how they want to um, seeking for collaborations and what's the questions they are interested. So please feel free to leave your own ideas over there, or if you met some points you are interested, you can just reply the notes below the notes. So by doing this, we're gonna to pick some of the ideas in the Padlets to form our following meetings of our clusters. So as everything is fresh for our clusters, um, at the beginning 2 or 3 meetings, we're gonna to invite some speakers to gathering people together and to warming up. But the form is flexible. If we have agreements for some specific topics, or we have like excellence ideas to produce some physical outcomes, we will probably change our formats of these meetings into a workshop, symposium, panel talks, things like that. So, as I mentioned at the beginning of the meetings, it's our first meeting. We are calling for volunteers who want to running the cluster, who want to contribute to these clusters. Um, we have a chair position uh, waiting for your applications, and community fellows waiting for your applications. So we want to build the relationship with agricultural and climate communities and seek experts and to co-develop the effective data systems and solutions on it. So, Pei, do you want to like elaborate more on your data, how you're gonna expect to collaborate with other researchers based on the the data set of these articles? Like which aspect you are expecting and you are designing for?
yeah. So currently we are, because this work is circa 2020, so we expect to extend to annual, but that's very challenging because that involves a wide range of the activity data. Um, the second part is to develop a more special explicit measurement data, say the water management for rice, even the fertilizer. If we can have pixel level fertilizer, manure, and the residue, that could further refine the estimations. So that's on the input data development. And the words on methodology part, now we are applying the IPCC approach, which is like tier 1 or tier 2. Maybe later on we can improve that methodology to tier 3 using model or machine learning AI approach. Yeah, there are a lot of work can be done to improve this work.
Okay. Thank you, Pei. I think we have. Okay. So,
I have to hop off, but I put some thoughts in the chat. So
all right. Thank you,
really
Lindsay.
looking forward
Yeah.
to the conversations.
All right. Thank you, Lindsay. Right now I'm sharing the screen of the Padlet, so you can just click the link and join the website to leave over what's your sort, and you can vote for the ideas people have already put out there. For the next meetings, we have already invited another speaker. I will send the flyer in the. Sorry, probably I cannot do that. Okay. I will give the next meeting will be the third Thursday of May. So our monthly meeting will be the every third Thursday of each month. So the topic of next meeting will be map carbon dynamics and greenhouse gas emissions towards transforming management practice to climate smart agriculture. The guest speaker is Yao Yongfa from Virginia Tech, who is a new PI from VT. So we're going to have him to introduce his researches on May 21. So it's the same time from 1 p.m. to 2 p.m. Eastern time. If you join our Slack channels or the email list, we will update you the reminder for our monthly meetings. So before we end up these meetings, is any other questions or suggestions for the clusters? Okay, I think we're good. So if you want to advertising these clusters, we have YouTube channel. You can refer to the talk of Peiyu. So I think it's time for us to now. And thank you, Pei, for joining us today to sharing your research. And I'm so glad to have you today.
Yeah, thank you for the invitation and very nice to meet all of you.